The lake is black under moonlight. Nothing burns, nothing shakes. There is no orange glow on the horizon, no lava at the shore, no bomb falling from the sky. The water looks heavy and silent, a dark surface lying between steep slopes and a sleeping valley. Then the center of the lake changes color. A pale circle appears. At first it looks like mist touching the water. Then the circle widens, bubbles race upward from somewhere deep below the surface. Too many to count, rising as if the bottom of the lake has suddenly opened. The black water turns gray. The gray turns white. The surface begins to boil upward. Not with heat, but with gas. A wave of foam rolls outward. The lake is not exploding with fire. It is exhaling. A pale cloud spills over the shoreline. It does not rise like smoke. It sinks. It slides low across the ground, pouring into the dark grass and between the trees. The cloud follows the shape of the valley because the gas inside it is heavier than the air around it. It moves like water, but it is not water. It is breathless air. The danger is almost invisible. A flame would warn you. Ash would blacken the sky. A flood would roar. But carbon dioxide can arrive without color, without heat, without smoke, and without the smell of burning. It can push oxygen away from the low places where people and animals breathe. The lake does not need to set anything on fire to become deadly. The terrifying part is that the disaster begins long before the surface changes. For years, a deep lake can look peaceful while gas is building in its lower water. At the surface, wind may ripple the water, rain may fall, sunlight may strike the shallows, fish may move through the upper layers, but far below, under the weight of all that water, carbon dioxide can dissolve into the depths and remain trapped. Pressure is the lock. A deep lake is not the same from top to bottom. Near the surface, the water is under less pressure. Deep down, the water is crushed by the weight above it. Gas behaves differently there. Carbon dioxide can stay dissolved in cold, deep water much more easily than it can in shallow water. The deeper the water, the tighter the seal. Bottle of soda works the same way in miniature. Inside the sealed bottle, carbon dioxide is dissolved under pressure. As long as the pressure stays high and the liquid is not disturbed too much, the gas remains hidden. Open the cap, shake the bottle, or lower the pressure, and bubbles appear suddenly. The gas expands as it rises. What looked still becomes foam. A gas-rich lake can become a giant version of that bottle. But there is one important difference. A soda bottle is sealed by a cap. A lake is sealed by its own depth, its own layering, and the quiet separation between the upper water and the lower water. If the lake is deep, if the bottom water is rich in carbon dioxide, and if the layers do not mix easily, the lower water can store a huge amount of gas. Not every lake can do this. Most lakes mix often enough, or do not receive enough carbon dioxide, or are too shallow, or have conditions that allow gas to escape gradually. The dangerous kind is more specific, deep, stratified, gas-rich, often in volcanic regions where carbon dioxide can seep into the lower water from beneath or around the lake. The risk belongs to a narrow set of conditions, not to every calm body of water. The surface can be misleading because the surface is not where the danger lives. The upper layer may be oxygenated, lighter, and more exposed to wind. The deeper layer may be colder, denser, and isolated. Between them can be a barrier, a zone that resists mixing. Scientists call this kind of layering stratification to the eye. It is all one lake, physically. It can behave like stacked liquids. The bottom layer becomes a hidden reservoir. Carbon dioxide enters that reservoir slowly. It may seep from volcanic rocks. It may come from geologic sources beneath the basin. Once it dissolves in the deep water, pressure helps hold it there, year after year. The concentration can rise. The lake does not need to rumble. It does not need to steam. It can keep storing gas quietly beneath the calmest possible surface. Then something changes. The trigger may not be dramatic. It could be a landslide into the lake. It could be a storm that disturbs the layers. It could be cooling surface water sinking and disturbing the deeper water. It could be a small seismic event. In some cases, the exact trigger may remain uncertain. The key is not that the trigger must be huge. The key is that it moves gas, rich deep water upward. That first upward movement is enough to start the chain. As deep water rises, pressure decreases. Lower pressure means the water can no longer hold as much dissolved carbon dioxide. Bubbles begin to form. Once bubbles form, the rising water becomes less dense. Less dense water rises faster. As it rises faster, pressure drops even more. More bubbles appear. The process accelerates. This is the runaway moment. Small release can pull more gas. Rich water upward. That water releases more gas, which makes it rise faster, which pulls more deep water behind it. The lake begins to overturn. The hidden reservoir that stayed trapped for years suddenly finds a pathway to the surface. Bubbles expand, water churns, the surface turns white. The lake is no longer a quiet basin. It has become a gas release machine. The visual sequence is violent, but it is not a volcanic eruption in the usual sense. There may be no fresh lava, no ash column, and no explosion of molten rock. The explosion is the rapid expansion of dissolved carbon dioxide as it escapes pressure. The water foams because gas is leaving it. The lake appears to boil, but the energy is coming from expansion, not from heat. The surface can rise, foam can surge outward. Large release may even push water aside and send waves toward the shore. But the deadliest part is not the water. It is the cloud that follows. When enough carbon dioxide bursts out of the lake, it can form a dense gas cloud above the surface. Carbon dioxide is heavier than normal air, so it tends to sink and flow into low areas if the air is still. That is why valleys matter. A lake sitting above or beside low ground can send gas downhill. The gas does not need to be hot. It does not need to be visible. It can hug the ground, fill depressions, and settle where people and animals are sleeping. In low concentrations, carbon dioxide is part of normal air. In high concentrations, it becomes a suffocation hazard because it displaces oxygen and disrupts breathing. The body notices oxygen loss too late. The danger is not like smoke filling the lungs with soot. It is the absence of breathable air. If oxygen is pushed away and carbon dioxide becomes dominant, a person can become confused, weak, unconscious, and unable to escape. Animals close to the ground can be especially vulnerable because the dense gas stays low. This is why the phrase exploding lake is both dramatic and incomplete. The lake is not exploding like a bomb. It is releasing a stored gas burden in a sudden overturn. The disaster is chemical, physical, and geographic at the same time. Chemistry dissolves the carbon dioxide. Physics traps it under pressure. Lake layering keeps it isolated. A disturbance releases it. Gravity sends the gas cloud downhill. The most famous modern example is Lake Nyos in Cameroon. In August 1986, Lake Nyos released a large cloud of carbon dioxide. The disaster killed more than 1,700 people and many animals in surrounding low areas. The event became one of the clearest warnings that a lake can hold a hidden gas hazard. It was not a story of fire or lava swallowing villages. It was a story of a crater lake releasing breathless air. Lake Nyos, also in Cameroon, had suffered a smaller carbon dioxide release 2 years earlier, in 1984. Together, these events changed the way scientists looked at deep volcanic lakes. The question was no longer only whether a lake looked calm. The question became what was happening in the layers below the surface. How much gas was dissolved? How stable was the stratification? Could the lower water rise? Could the lake release gas faster than it could safely escape? The lake surface gives almost no answer by itself. A dangerous lake may look ordinary. There may be no obvious bubbling at the surface for long periods. The disaster depends on conditions hidden in depth profiles, temperature, density, dissolved gas content, and the structure of the water column. To understand the lake, scientists must measure vertically, not just look horizontally. Picture the lake cut in half. At the top is a layer of surface water touched by wind and daylight. Below it is a darker layer that does not easily mix with the top. Deeper still, near the bottom, carbon dioxide is dissolved under high pressure. The gas molecules are not sitting as big visible bubbles. They are held in the water itself, invisible until pressure changes. Now picture a pocket of that deep water being lifted. Maybe a slope collapses underwater. Maybe colder water sinks from above. Maybe a disturbance pushes deep water upward. At first, the rising water still looks like water. Then tiny bubbles appear. The bubbles reduce the density of the water. The rising column becomes buoyant. It pulls more deep water upward like a chimney. The chimney grows. Bubbles expand as they climb. The deeper water releases more carbon dioxide. which makes the water column rise even faster. The lake becomes a self-amplifying system. The first bubbles are not the end of the event. They are the trigger for more release. This is why the surface can go from calm to violently foaming in a short time. The whiteness is a clue. White water at the surface means the lake is full of bubbles. The same way a shaken carbonated drink becomes pale and frothy. A gas-rich lake can turn white when dissolved gas escapes rapidly. In the opening image, the lake looks as if it is boiling, but there is no need for boiling temperature. It is the sudden expansion of carbon dioxide that fills the water with foam. The gas cloud then changes the scale of the disaster. A release at the lake's surface is dangerous. A gas cloud moving into a valley is worse. It extends the hazard beyond the shoreline. It turns topography into a pathway. Low ground becomes a channel. A sleeping valley becomes a basin for air that no longer contains enough oxygen. The cloud may be pale if it carries water droplets or disturbed mist, but carbon dioxide itself is colorless. That matters because the most dangerous part may not look like a thick cinematic fog. A person in its path may not understand what is happening. There may be no flames to run from, no smell of smoke, and no visible wall of water. The air itself changes. The silence is part of the horror. Explosions in movies announce themselves with sound and light. A Limnic eruption can be deadly because it does not behave like the disasters people instinctively recognize. There may be churning water at the lake, but farther away, the cloud can move low and quiet. It can reach places where no one sees the surface foam. The mechanism also explains why the danger can persist after the first release. If a lake continues to receive carbon dioxide from below, it can recharge over time. The deep water can become gas, rich again unless the gas is safely removed or the lake is monitored. The disaster is not simply one accident from the past. It is a warning about a system that can rebuild pressure if the conditions remain. That is where degassing comes in. A degassing pipe is a controlled way to do what the disaster did. Suddenly, it reaches down into gas, rich, deep water and brings that water upward through a pipe. As the water rises inside the pipe, pressure decreases, gas comes out of solution, and the gas bubbles help lift the water column. A plume of gas and water can spray upward at the surface. It looks dramatic, but the goal is prevention. Instead of letting the lake release gas all at once, engineers try to vent the carbon dioxide gradually. The pipe becomes a safety valve. It lowers the gas burden in the deep water over time. The idea is not to drain the lake, but to reduce the amount of dissolved gas that could fuel a runaway eruption. The image is unforgettable. A pipe stands on a floating platform. Water erupts upward in a white fountain. Gas escapes into open air in a controlled stream. The lake is still powerful, but the release is no longer hidden. The invisible pressure has been given a path. Monitoring is just as important. Scientists can measure dissolved gas concentrations at different depths. They can track temperature and density layers. They can look for changes in the lake's stability. They can study whether degassing is reducing the gas inventory. The lake's danger is not judged by beauty or calmness. It is judged by what the water is storing below. The hard part is that the disaster mechanism is counterintuitive. Water feels like the opposite of explosion. Lakes feel stable. Deep water feels safe because it is hidden and still. But stillness can be part of the trap. If layers do not mix, the lower water can become isolated. If gas enters that isolation, pressure can preserve the danger. Calmness becomes the lid. The same calm surface can mean different things in different lakes. In an ordinary lake, calm may simply mean no wind. In a deep stratified volcanic lake, calm may also mean the layers are undisturbed. The visual surface does not tell the whole story. The lake has a vertical life. Its danger depends on depth. This is why it is wrong to say that lakes generally explode. They do not. The conditions are rare. The known modern disasters are associated with specific kinds of deep, gas-rich lakes. A shallow pond cannot become Lake Nyos simply because it is quiet. A large lake with strong seasonal mixing may vent gases gradually. A limnic eruption requires a particular combination: gas source, deep water, stratification, pressure, and release pathway. That specificity makes the real phenomenon more frightening, not less, because the danger is not random magic. It is a physical system with rules. It can be studied, it can be monitored, it can be reduced. But when the rules line up, the result can look impossible. A lake that releases a killing cloud without flame return to the night image. The center of the lake foams. The white patch grows. The surface churns as deep water rises. Bubbles burst. A low cloud spills outward. The cloud does not climb into the sky. It pours into the valley. The shore disappears. The trees near the water vanish into pale vapor. The lake has become a source of air that cannot be breathed. Now slow the image down. Every bubble that reaches the surface began as dissolved gas under pressure. Every pale streak of foam marks a place where carbon dioxide escaped solution. Every movement of the cloud follows density and gravity. The scene is not supernatural. It is a chain of ordinary physics operating at disastrous scale. The lake stored the gas because deep pressure allowed it. The layers preserved the gas because they did not mix. The trigger released the gas because water moved upward. The upward movement accelerated because bubbles made the water lighter. The cloud moved downhill because carbon dioxide is denser than air. The disaster felt sudden because the visible part came last. That last point is the key. The lake did not become dangerous when the first bubble appeared. The danger had been building quietly beneath the surface. The eruption was the moment the hidden system became visible. The visual violence was only the final sentence of a story written in deep water. A cross-section of the lake tells that story better than any surface photograph. At the bottom, carbon dioxide accumulates above it. Dense water holds it down. The middle layer resists mixing. The surface gives away almost nothing. Then one rising plume opens a path. Bubbles expand. The plume grows. The gas-rich bottom water follows. The lake overturns. The surface erupts white. The gas cloud leaves the lake behind. This is the part that makes limnic eruptions different from many water hazards. A flood carries water. A wave pushes debris. A limnic gas release can move through air. The danger can travel into valleys and depressions even after the water itself has calmed. The lake may return to stillness, while the gas cloud remains the immediate threat below. Morning can make the scene look impossible. The water may become calm again. The surface may darken. The foam may fade. The valley may look still. Without measurements and memory, the lake can seem innocent. That is why the afterimage is so disturbing. A peaceful lake can be the same place that released a deadly cloud hours before. Science does not remove the horror. It changes the shape of it. The horror is not that the lake is mysterious in a magical sense. The horror is that the mechanism is understandable, silent, and hidden. A disaster can be built from solubility, pressure, density, and gravity. It can be held for years by the weight of water. It can be released by a disturbance that seems too small for the consequence. The prevention image is the opposite of the disaster image. Instead of one sudden white eruption across the entire lake, a degassing pipe releases a controlled fountain. Instead of an invisible cloud rushing into a valley, gas is vented gradually into open air. Instead of years of hidden accumulation, measurements track the burden. The same physics becomes a tool rather than a trap. But prevention depends on attention. A dangerous lake cannot be judged once and forgotten. Gas can continue to enter. Layers can change. Equipment can age. Communities below the lake need systems that treat the calm surface with respect. The goal is not fear of every lake. The goal is understanding the few lakes where silence may be storing pressure. The final image returns to the water. The moon is gone. The surface is calm again. A degassing fountain rises in the distance, white against the morning, releasing pressure slowly instead of all at once. Below the platform, deep water still carries memory in its layers. Above the shore, the valley is quiet. The lake looks peaceful. That is exactly why it must be understood. A lake can explode without fire because it is not fire that makes the blast. It is stored gas. It is pressure. It is stratified water holding carbon dioxide in the dark until one path upward turns the whole lake into a shaken bottle. The surface may be calm, but in the wrong kind of lake, the deepest water can be waiting to breathe.